My presentation today is called Milestones in Artificial Intelligence, or Why High School Math is More Relevant Than Ever. And I gave this presentation a little over a month ago to a group of high school kids. Um, and I thought it might be interesting for other people as well. So I figured I might as well just give the same presentation to you guys. Um, I have not edited it in any way since then, so some things might already be a little bit out of date. Things are moving fast in that era, but anyways, so let me uh, let me start. Let me see. So we're gonna start off with a little introduction about thinking machines. After that, we take a quick look at the math behind today's artificial intelligence. We'll look at some highlights of AI development, and then at the end, finish up with some outlook and challenges. So with that said, let's jump right in here. So for that, let me first take you back to the year 1950. The man that you see down there in the picture is called Alan Turing. He is 37 years old at that time, an English mathematician and computer scientist. Um, there is a computer up on the left side. This is what a computer in 1950 would have looked like. They were called electronic delay storage automatic calculators back then. So basically automatic calculators. But anyways, so this Alan Turing, everybody knows hopefully who that is. He played a major role in the development of computers. He is also called the father of theoretical computer science. And he is already in 1950 thinking about intelligent machines. And he actually said that machines should be taught rather than programmed back then. And he also came up with a test to determine whether a machine can think or not. And this test is called the Turing test. And it goes like this. There's this person who chats at the same time with a human and a computer. And basically, if the person cannot distinguish between who is the human and who's the computer he's talking to, then we say that the computer has passed the Turing test, more or less like this. This is how it goes. So sadly, Turing did not get to chat with the computer during his lifetime, and it took another 16 years to actually chat with the computer. And this was in 1966 when Joseph Weizenbaum, a German computer scientist, created the first chatbot, Eliza. And Eliza emulates a psychotherapist. Actually, I have a demo, but I'm not sure that's going to be complicated. I'm not going to go through the demo. I'm just going to go through to a sample output here of Eliza. So in 1966, you could chat with a computer like this. Eliza would ask you, is there something troubling you? You would answer something, men are all alike. Just maybe you take a quick moment to read this conversation here. I played with Eliza when I was like maybe 13, 14 years old. It was amazing back then. It was interesting. Um, you can quickly figure out that you're not talking to a person, but in 1966, this was something new, and some people actually did think they talked to a person, but Eliza did not really pass the Turing test because you quickly come to its limits. Um, Now, let's fast forward to today. Can machines think now? So today we have ChatGPT, and ChatGPT is said to have broken the Turing test. Um, Apparently, people prefer to talk to a machine because it's more polite, it's more knowledgeable. Um, and actually, this image here on the in the middle, down in the middle, in a showdown of psychotherapists versus ChatGPT, the latter wins. New study finds that image I added, a couple of days ago because I stumbled across this article. Um, so so apparently, we do want to replace those psychotherapists, sooner or later. Anyways, so yeah, again, back then, you could identify the machine because the answers were not really consistent or not really, you know, uh, conversational. They were weak, and today's answers from a machine are much stronger, much better, much more knowledgeable. So, we might prefer those. Does that mean that machines can think now? Well, this conversation in this picture here on this slide is a conversation with a chatbot called DeepSeek. You've probably all heard of DeepSeek by now. Um, DeepSeek is supposed to be good at simulating the thought process of a human. Um, and that we also call reasoning. That means we gather facts, we explore ideas, we draw conclusions from those ideas. Um, so in this slide, I kind of highlighted a couple of sentences where it says, "Let me think about how these characters might interact." So let's go to the prompt first. A joke about a pelican and a walrus who run a tea room together, and the answer from DeepSeek is okay. Blah 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 blah. Let me think about how these two characters might interact. Further down, it says, perhaps the walrus could be a bit clumsy, or maybe there's a play where whatever. And I also think about the setting of a tea room. So it simulates the thought process of a human. But does and DeepSeek really think at that point? Well, I guess it's debatable to say the least. I guess we all would answer the question with no. A computer cannot think. Um, but I guess if we go a little bit deeper, I mean, the question really is what is thinking? Um, and we do not want to think that thinking is as simple as what a computer can do right now. But what if it is? What if our thinking is similar to what a language model today considers thinking, just that we have a little bit more sensors and experiences, I guess, that play into our thinking or into our results. Maybe the actual um, process is not very different. I don't know. I leave it for you to decide. Anyway, so the conclusion here is the today's AI can simulate the aspects of thinking. Um, they're not really considered thinking machines, but we are already working on the next iteration, which is called artificial general intelligence. We want to get to machines that can think, reason, and learn like humans eventually. Let's see if we get there or not. To be determined. So that was the motivational part. Again, I gave this presentation to some high school kids. So, I am myself a father of two high school kids. One not anymore, but recently. Um, Myself, I actually started working with AI in 1990. Did a PhD project a little later, end of 1990, also involving AI. Um, so I have some background, but you know, uh, anyway. The reason that I gave this talk to those high school kids was because I had a conversation with my kids about AI in school, and I said, "Did you ever talk about AI in school?" And they said, "Yes." And I said, "Nice. What exactly did you talk about?" And they said, "Not to use it." Um, which is sad because the modern AI is based on relatively simple math that you can learn in high school, that is taught in high school, actually. So, my son, in his senior year of high school, he had linear algebra and multivariable calculus. Um, but he didn't really know what to do with this linear algebra. And linear algebra and multivariate calculus are the backbone of today's artificial intelligence. And we're going to go into this real quick in a second. Um, First of all, before that, we just take a quick look at what exactly artificial intelligence is. So artificial intelligence has different subfields, one of which is machine learning. Machine learning includes like the traditional machine learning things like linear regression, random forests, support vector machines. All that is like this traditional machine learning. And it also includes neural networks, and the field of neural networks includes the field of deep learning. And deep learning is why today's AI has become so interesting or successful. And we're going to look into this a little bit. So before we do that, is there any questions or concerns? Let me see if I can find the Zoom window. You all still with me? I can't see you move.
Yes, sir.
Okay, good, good. All right, awesome. Let me find this other window again. Okay, yeah. So, all right, what is a neural network? So what you see here is an image of a brain. And a brain has approximately 86 billion neurons that process and transmit information. And these neurons enable us to think, move, and feel. So imagine this brain here. The person with this brain just looks at an image with a cute dog, and this is what happens in his brain. Like something gets triggered there. Um, so already back in 1958, scientists thought about simulating a brain. Um, you can see here on the top, this is a biological neuron. It has dendrites, I hope I pronounce that right, which from the input of the neuron, it has a cell body that collects the information that comes in, and it has an axon which transmits outgoing information to the connected neurons. The bottom picture is a computer version of it. Again, we have inputs, we have a some symbol there that kind of collects the information. The F is a function that decides what gets transmitted, and then we transmit something, or we might not transmit something. That's the artificial version. Again, that is already in 1958. People think about those things. Um, the math of this artificial neuron is rather simple. We have inputs x1 to xn that get weight weighted by individual weights. Um, our collector of the information is the sum of the weighted input. We have an activation function that decides whether or not this neuron will transmit information to the next neuron. And in this case, it's a very simple activation function. We say if the weighted sum is above 0, then we transmit a 1. And if it is below 0, then we transmit a 0 or no information to the next neuron. Um, So with that said, we can build an artificial neural network by just um, you know chaining together a couple of artificial neurons. So in this case here, we still have our input x1, x2, x3, um, and our artificial neurons here are h1 to h4 and y1 and y2. This little artificial neural network here gets, for example, as an input, the pixels of an image, and the goal is to decide whether or not this is a cat or a dog. And if it is a dog, then Y2 would spit out a 1 at the end, and Y1 would spit out a 0. And if it's a cat, vice versa. Y1 would spit out a 1, and Y2 would spit out a 0. Again, the math is quite simple here. We, again, sum up the weights for each neuron, the weighted input for each neuron, um, apply a activation function, and then continue with the results into the next neuron. So from H1 to Y1, uh, or to Y1 and to Y2, the output of H1 would flow into the input of Y1 and Y2. Make sense? So it's rather simple math in this case here. Now, what is a deep neural network? A deep neural network is a network that has more than, like this particular network here has had this one hidden layer and this output layer. A deep neural network has more than one hidden layer, basically. Obviously, there's more complicated architectures that are used today, but generally speaking, a deep neural network is just defined to be a artificial neural network that has more than one hidden layer. And if we translate this weighted sum of the inputs um, into a little more readable form, we will see that this translates actually to a vector and matrix multiplication. So, our x1, x2, x3 gets multiplied with the weight matrix that flows into this the first hidden layer here. So it's just a rewriting, just to make it a little look a little simpler. It's the same math. Um, Again, H1 after this matrix multiplication, we end up with H1 dash, H2 dash, and so on. That still needs to apply the activation function. But after that, we have another vector matrix multiplication in the second layer and the third layer, and so on and so forth. So basically, what we see here is linear algebra. It's a multiply a vector with a matrix multiplication, vector multiplication. We can learn this in high school. Is all that I'm trying to say with this. Um, Obviously, if we have this network here and we want to decide whether or not the input is a cat or a dog, we need to adjust our weights here. The input is always going to be the pixel of the image, but what varies, or what we can change here is our weights. So we need to find a set of weights so that our output gives the correct results. And if we don't have the correct weights, then our output has errors. But what we can do is we can look at the error function with respect to our weights, and we can calculate the gradient of the error function, so that we can adjust our weights in the direction of the descending gradient here, um, so that our error ultimately gets minimized if we change our weight. So we adjust our weights such that the error of our network, meaning that the erroneous classifications in this case, would be minimized. And this is the training. So um, that basically means, right, that the foundation of modern AI, or of deep neural networks, if you want it, is linear algebra and multivariable calculus in this case, but calculus, gradients and vector and matrix multiplication. All right, I'm gonna stop again here, see if there's any questions. Let me see if I find the window. Where's Zoom? So, hey. All right. All right, I'm on time. All right, that looks good. Cool. So continuing, um, so deep learning, so the training of deep neural networks, has been invented a long time ago. 1950, 1960, the theory was already there. But the problem always was that there was not enough computational power to actually do something useful with it. Um, and only the rise of the GPUs made deep learning again attractive and practical and successful at the end. Um, so, but that only happened in 2012, when the first um, deep network successfully was trained. The network was called AlexNet. Um, AlexNet is an image classifier. Again, you put in an image, you get out what is on the image. It has 1,000 possible outputs, not the two that we saw, but 1,000 possible outputs. Um, and it has about 60 million parameters. And this was actually in 2012 was the first time that a deep neural network was trained by leveraging GPUs for training. Um, and this AlexNet that won a competition, which is called the Large Scale Visual Recognition Challenge, by a huge margin. And this is a kind of an example here. You get like some image, and you need to classify what's on the image. And this is kind of the result that AlexNet gives on those different images here. So behind AlexNet was a British computer scientist named Geoffrey Hinton, who is now called the godfather of AI. Hinton was already training neural networks, or deep neural networks, in 1986. It didn't kind of take off again back then. Computational power and the data was not kind of data maybe, but the computational power wasn't quite there yet. And it was only in 2012 when he successfully did that. Hinton won the Turing Award in 2018, which is also considered the Nobel Prize for Computer Science, for his work on deep neural networks. And last year, he won the Nobel Prize in Physics for his discoveries, that enables machine learning with artificial neural networks. So yeah, that was Geoffrey Hinton in 2012. Short after that, deep learning is taking off. Other players enter the scene. We have DeepMind in 2015, until then rather unknown. They developed an AI system called AlphaGo, which was able to defeat some of the world's best professional Go players. Um, and Go is considered one of the world's most complex board games. Apparently, it has more legal game positions than atoms in the observable universe. Okay, so that's quite a bit. Um, this was something back then was thought to be still decades away. Um, but AlphaGo showed how deep learning combined with reinforcement learning could achieve human-like strategic thinking. And yeah, so deep learning, one of the keys to train AI to play Go. Um, and DeepMind strikes again 3 years later with this AlphaFold. Um, so AlphaFold predicts the shapes of proteins. The shape of a protein determines how the protein works. Understanding the structure is essential for drug discovery and for uh, um, drug development. And until then, before 2018, well, before AlphaFold, um, we or like the scientists had determined the shape of 170,000 proteins, mostly via X-ray or microscope, very time-consuming things. And suddenly, with AlphaFold, we now know the shape of 200 million proteins. So it's 170,000 versus 200 million now. Um, and this AlphaFold actually helped during COVID to understand the COVID virus better, and is also currently used to speed up, early phases of drug discovery. Um, so last year, AlphaFold 3 was announced that now predicts the shapes of all elements of life, which are proteins, DNA, RNA, small molecules. Um, um, and yeah, this apparently helps to understand how all molecules of life work together, which sounds pretty awesome. Um, you know, uh, and last year, the CEO of of DeepMind, which is the company behind AlphaFold, and the director both won the Nobel Prize in Chemistry for their work on protein structure. Um, yeah, so that was that. Um, on the other hand, we can finally chat with the machine. Um, uh, and this is kind of a little bit the history of GPT, of ChatGPT, the transformer architecture that revolutionized NLP, NLP, natural language processing. I worked actually in natural language processing before, 2017. Um, all that was all the tools and processes that were used back then. You can basically forget all about that. Nobody uses them anymore. Everything is now transformer based. And yeah, so we have 2018 GPT-1 with 117 million parameters, and then 2024 we have GPT-4, which has what is that? Guess like a trillion parameters, 10 times 175 billion. Um, Anyways, so there's other projects in the natural language space. There's Google MedPalm LLM, which is mm, a language model trained on medicine. So it's like your personal doctor kind of thing. Um, And there's also some efforts going on. There are some efforts going on to understand uh, animal speech. One of which is here the sperm whale communication project. There are projects about understanding, dog communication. Yeah, not really natural language, but a little bit related, maybe, maybe not. Okay. Um, so in terms of computer vision, after AlexNet, also computer vision, the field of computer vision has exploded. Um, we now use computer vision, in in medicine quite a bit to detect tumors. There is actually a project to detect diseases from the image of an eye. Just just by the taking a picture of the eye, you can detect diseases. Um, you know, it helps to diagnose patients analyzing X-rays or CT images, and it helps the doctors to enhance the images, just for them to interpret better. Um, so this is how AI helps in computer vision, uh, or in medicine, actually. How computer vision helps in medicine. Sorry. Um, There is the field of robotics also that I just want to briefly touch on. We have self-driving cars that apparently are very awesome. I have never been in a Waymo myself, but people tell me it's an awesome experience and it feels very safe. Um, there are these awesome robots by Boston Dynamics that you see here in the middle picture. That also use deep learning, for some of their actions or interactions. We have AI-assisted surgery, another, robotics example of today's AI. Um, so this is more or less what I, was going to touch on. The highlights of, today's AI, or like how did we get where we are today. Um, we have today AI systems that are excellent at like very task specific things. They perform exceptionally well in areas like computer vision and natural language, in games, and robotics. But they still lack the true general understanding that goes beyond what they were trained on. Um, yeah. I guess the next goal, I already said it, is, this artificial general intelligence that, especially Sam Altman is talking a lot about. Um, that is about understanding, the world beyond the statistical patterns in the data, making decisions like humans make decisions to handle ambiguity and complexity, learn from experience without the need of retraining. That's a big one, actually. Uh, adapt to new tasks and domains. So this is all part of this artificial general intelligence. Um, And there are certainly some challenges right now and in the future. Um, we AI must make decisions that are aligned with human values. Back down in this picture on the right side, you can see the thing is called the trolley problem. The trolley problem, is uh, there is this trolley that goes straight. And if it goes straight, it will kill those one, two, three, four, five people that are on the tracks. But there's this person that can switch this, or can change the direction of the trolley to go up. And in that case, it would only kill one person. And the trolley problem is like, is it like what should the person do? Should the person do nothing and allow the trolley to kill those five people, or should the person pull the trigger or like switch or change the direction of the trolley um, so that only one person is killed? But that would mean that the person like um, interacts or is part of this killing process, basically, more or less. Um, so, I mean, you can read about the trolley problem, but this is kind of also like a problem with AI and self-driving cars, I guess. Also, like, should I steer, like, if I have two options to cause an accident, which one is the least mm, damaging one, I guess. Anyways, yeah, and another issue with AI, or another interesting aspect of AI, is that we can't, oftentimes we cannot explain why certain things, why the AI outputs certain things, why certain, um, so the AI is a black box for us. We don't know why certain things happen, and moreover, it's also interesting because, like in the context of like thinking AIs or like reasoning AIs, I've heard stories about having to align those models to form their thoughts or to simulate the thought process so that a human actually can understand it, because they also could just go and form completely not understandable thought processes to come to a similar or maybe a better conclusion, but that we wouldn't understand. Um, anyways, so some things uh, to think about, or some interesting aspects of AI. Also, like there was um, this project or this thing one time there where two AIs kind of talked to each other, and when they figured out that they were both AIs, they kind of didn't use words anymore, but used some other things to communicate. Anyways, I don't have any sources for that. It's just something in my head right now that I remember. Yeah. Sorry. With that said, that's all I have. Thank you. Any questions or comments?